apply that to two important concepts, the movement of water, as well as absorption and secretion across the epithelial cell layer. Okay, so we'll start out by looking at how different solute concentrations across the membrane can influence the movement of water, and then we'll talk about the difference between osmolarity and tonicity of solutions. Okay, so let's start by defining osmosis. So what is osmosis? It's basically the movement of water through a permeable membrane. Okay, now water, just like solutes, right? We talked about our concentration gradient of solutes. Water is the very same way. It will move according to its concentration gradient. So water will move from an area of high water concentration to an area of low water concentration. Now, in terms of the big picture, we want to understand that an area of high water concentration is synonymous to an area of a low solute concentration. So another way that we can describe osmosis is the movement of water from low solute concentration to high solute concentration. Okay, now the movement of water is always passive. Okay, that can be implied by the fact that it's always down the concentration gradient, and it is affected by membrane potential. So this is not an ionic force. This has nothing to do with the membrane potential, nothing to do with any charge. Water is not a charged particle. And so this is movement unaffected by the membrane potential. And like I mentioned earlier, this is driven by the water gradient. So based upon different solute concentrations, we have a gradient of water, and water moves along its gradient. Okay. So let's start out by kind of just summarizing this and illustrating this a little bit. All right, so speaking about osmosis, and we defined osmosis as the passive movement of water you can then refer to it as the diffusion of water. Right, remember, diffusion is a passive movement across a membrane. We said that it is not influenced by the charge on the particles or the polarity of the cell, right? Not influenced by the membrane potential. And then water is moving from its high concentration to low concentration. Okay, so let's look at two solutions here. So we've got two solutions. Let's describe the relative osmolarity of both of these solutions. So let's describe the number of solutes associated and the amount of water. And then we're going to look at that relative. So we're going to look at the solute and water concentration inside as well as outside here. Now, really important, we want to point out that the membrane in question, so the membrane of this, let's say it's a cell, is impermeable to the solutes that we're going to describe shortly, right? So the membrane is impermeable to the solutes in question. All right, so on the first side, in this first solution, we have pure water outside, so there are no solutes outside, and then there are a few solutes dissolved inside the cell. All right, so we got 1 molar of solution dissolved inside and 0 molar solution outside. And as far as water goes, we have 100 molar inside, and because we have much more water outside, let's say it's 102. Right? So basically we have a solution outside of the cell that has all water and no solutes, and a solution inside that has water and some solutes dissolved. Okay, let's compare that to another solution where we have solute particles dissolved outside. So there's particles dissolved in the solution outside, as well as solutes or particles dissolved in the solution inside. And so our numbers change here a little bit. We have 1 molar of solution here, 100 here inside, but then on the outside, we also have some particles dissolved. So our concentrations change slightly. Okay, so now we're going to look at what water will want to do in terms of its concentration gradient. So in this first scenario, do we have a driving force for the movement of water? Bless you. Do we have a driving force for the movement of water in the solution on the left? So we got a membrane that's not permeable to the solute. We have no solute outside, and we have lots of solute inside. So do we have a driving force for the movement of water? Is there a gradient in terms of the water concentration? There is, right? Where's water at its highest concentration? The outside or inside? Outside, right? So there's the higher water concentration outside, a lower water concentration inside, and so we have the movement of water, again, passively into the cell, from high concentration to low concentration, okay? Now in the solution on the right, we have solute concentration both inside and outside the cell. So now we're going to have to decipher where we have the higher water concentration. So where is that? Based upon our osmolarity solutions down here. Inside, right? So we got a higher water concentration inside the cell and a lower water concentration outside the cell. So we have the passive movement of water out of the cell. Okay. And this describes the driving force for the movement of water. Okay, so we're not necessarily looking at the solutes in question. We're looking at water. Where is water the highest and where is it the lowest in concentration? And that is going to provide our driving force. Now we're going to move on to speak about the osmolarity or the osmolar pull or osmotic pressure. And that can be said because of this force. Okay, so because water naturally wants to move from high to low concentration, we can then describe that movement as a force. And you can quantify that force as the amount of pressure it would take to stop the movement of water. Okay, and that's what the osmotic pressure is, which we'll talk about. All right, any questions there? Any questions? Okay, so our two illustrations here are very similar to what we just drew, right? We have a difference in solute and water concentration, and so we can see the movement of water either into the cell in this case or out of the cell in the case down here because of differing solute and water concentration. Okay, let's now speak about osmolarity. So osmolarity looks at the total number of solute particles that are dissolved in a solution. Okay, so it depends on the type of solute in question, and it depends on whether it can further dissociate once it enters that solution of water. And so this is where osmolarity is different from moles. So moles is basically just the solute. So if you look at just the solute, we can say that there's 1 or 0.1 mole of glucose, or we can talk about 0.1 mole of sodium chloride. So it's just looking at the solute on its own, not dissociated in water. But if we took 0.1 mole of glucose and we put it into 1 liter of water, we would end up with a solution that had an osmolarity of 0.1 osmoles, because glucose is 1 molecule and it does not further dissociate. But if we took sodium chloride and we put 0.1 mole of sodium chloride into that same 1 liter of water, the osmolarity of that solution would be 0.2 osmoles, because sodium chloride would further dissociate into sodium and chloride. Okay, and because very importantly, because osmolarity looks at the total number of solute particles, we're going to consider that sodium as one particle, we're going to consider that chloride as one particle, and so the osmolarity of that solution would be 0.2 as opposed to 0.1. Okay, so that's a really important or really helpful example to show that osmolarity looks at the total number of solutes dissolved in their individual particles. Now, when we speak about the osmolarity of our body solutions, like saliva, blood, etc., we typically look at the fraction of a single osmole. So we talk about the milliosmole, like 1 in 1,000 of an osmole. And this is used to describe our body fluids, our physiology. And so we can then deduce that the osmolarity of our extracellular fluid and our intracellular fluid is round about 300. Some textbooks will say 280, but let's call 300 milliosmol in terms of those two solutions. Okay. Now it's really important that the ICF and the ECF are of the same osmolarity. We'll talk about examples of how that can change and how we can get some pathology. But for the most part, in healthy, normal physiology, the ICF and ECF are roughly 300 milliosmol. Okay, so based upon that discussion, we can then talk about different types of solutions. We can speak about a hyperosmotic solution and a hypoosmotic solution, and then an isoosmotic solution. So in an isoosmotic solution, which is where we like our physiology to be, where we like our solutions in reference to our cells to be, is where the number of solute particles in the ECF and the number of solute particles in the ICF are the same, and we have no net movement of water, right? So we have some flow of water, right? Water is moving out, water is moving in, but there's no net accumulation of water either inside or outside the cell, and so we can maintain the relative shape of that cell. In the case of one of our cells being immersed in a hyperosmotic solution, the solute concentration in the solution outside is much more than the concentration of solutes inside the cell. And so what we have is now a water gradient. So where will water move in the case of a hyperosmotic solution? Where will water want to move? So where's water at the highest concentration? Yep, that'll be inside the cell. So we got more water inside the cell, less water outside the cell, and so water wants to move outside the cell, and that gives us this crenation of the cell where it becomes really crumpled or shriveled, and that can lead to some pathology, especially if we're speaking about red blood cells, where they lose their shape and they lose their ability to carry oxygen. On the other hand, we can talk about a hypoosmotic solution, right? This is if we immerse one of our cells in a hypoosmotic solution, or a solution that has less solutes dissolved than what is dissolved inside the cell. And this leads to water movement in the opposite direction. So there's more water outside, less water inside, and this will lead to cell lysis. So as more water moves into this cell, it will swell until it eventually ruptures or lyses and